being here for Eric Spanton's thesis defense. I just checked my email messages, and I have 5,196 email messages that mention Spanton, which is almost a power of 2, but not exactly. And it just kind of shows the ability, how Eric has the ability to sort of square the abilities of the people around him. So since the first time that Eric wrote to me, which was in March of 2010, some of the other things that enter into our correspondence are his note to me saying, "No, I'm going to visit another school that day, so I won't be able to talk, unfortunately." And then another correspondence 6 months later where he asked me for a rotation. He was in the lab working with Lan Luan, who was a senior student, for a year or two before Vina Kaliski, who was the senior postdoc in the lab, asked if she could, if Eric could work with her, and taught him how to use Squid. And then he also worked with Katja Novak, who was the next postdoc in the lab, and then worked on some work that Yuhao Wang had done after Yuhao left. So Eric won't be talking about all the work that he did today, but just another factor of 2 thing is that of the 4 senior people with whom he worked very closely, not counting myself, he's shown that 1/2 of them had made serious errors in their work that Eric was able to correct for the scientific record. So hopefully that's a high peak on that correction career. And so you'll be telling us also with the power of 2 about 2 pieces of work today, I think.
Was
so,
that a challenge
Eric.
to your current students with this talk?
Oh no. Well, thank you for that very nice introduction. Yeah, so today I'd like to talk to you about a couple of experiments I performed, and here's a rough outline of the talk. So first, I want to give a broad introduction to why you want to study quantum materials. And I've put a unicorn here to indicate that one of the goals is to sort of realize things in materials that shouldn't exist in nature, but we can make them exist. And so one of the overarching, long-term goals is to sort of realize these unicorns of materials by doing physics. And then I'll give a brief introduction to the probe, which is that I use to look at quantum materials, which is scanning SQUID. And then I'm going to divide the rest of the talk into to talk about 2 experiments. First, I will talk about images of current flow in a material called indium arsenide, gallium antimonide. And then I'll talk about some recent work that I've been able to do on indium arsenide nanowire Josephson junctions, which probe how a superconductor and a non-superconducting material sort of interact, and how the superconductivity leaks into the non-superconducting part. Okay, so this is a broad introduction. I'm going to look at my parents. So electrons are a fundamental particle. And they have a set of numbers which describe their behavior. They have a mass, they have a negative electric charge, and they have a quantum mechanical spin that determines how big of a magnetic signal they produce, a magnetic moment, and also what happens to their quantum mechanical wave function when you interchange 2 particles. The interesting thing is that when you put these in a lattice, you can oftentimes think of the combination of the electron and the lattice as a quasi-particle that lives in free space. So this is, a theoretical construct that instead of thinking about both the electron and the lattice, we're just going to think that there's a particle in some sort of vacuum that has some different properties, a different mass, maybe a different electric charge. And so depending on what sort of atoms and what configuration the lattice is in, you can manufacture different types of quasi-particles. I'm going to give a very basic introduction to how the behavior of quasi-particles can fundamentally differ from that of electrons. So let's take a chunk of conducting material here in green and flow a current from left to right. And so if the quasi-particle is negatively charged, that corresponds to a negatively charged particle moving from right to left. Now if we apply a magnetic field, there will be a force on this electric particle, and I hope I've done my left and right hand rules correctly, that pushes the particle upwards. And so as you're flowing a current in a magnetic field, there will be a charge accumulation at one of the edges. And so if we measure the voltage drop between the top and bottom edge, we get a negative voltage, and this is called a Hall voltage. And this negative voltage tells us, looking at this equation here, that the sign of the charge carrier is negative, and this is often notated as the Hall coefficient. if we take, for some reason, assume that the charge carriers are positive, then we can draw the same picture and we see that the quasi-particle is pushed in the same direction, but now there's a positive accumulation on the top edge. And so if the charge carriers are positive, we should see a positive sign in the Hall coefficient. And even though the fundamental charge carriers of all systems that I'm going to talk about are electrons, the charge of the quasi-particle of the electron living in the lattice will sometimes act like it has a positive charge. And in fact, in the same material, by applying an electric field, you can see a Hall coefficient that goes from positive to negative, indicating that for some electric fields, the charge carriers in this material, bismuth, antimony, telluride, or selenide, acts like they have positive charge, and then as you apply an electric field sort of out of the plane, they can act like they have negative charge. And so this is something that's sort of mundane for condensed matter physicists, but it's actually quite weird that you can stick electrons into a system and then they'll sort of behave like a particle that has positive charge. And so the question is, what else can we change about this quasi-particle from how electrons normally behave? And it turns out a lot of things. For instance, the mass of the particle the quasi-particle can be anywhere from a small fraction of the bare electron mass to 1,000 times the mass in heavy fermion materials. Also, in some exotic materials in a magnetic field, you can get electric charges which are fractions of the normal electron charge. So there's really exotic stuff that can arise of just putting electrons in a lattice. And so now I'm just going to list off a couple more weird behaviors that are fundamentally due to electrons in lattices. And so ferromagnetism is one example. This quantum mechanical spin that I was talking about behaves a certain way for a free electron in a magnetic field, in that it's paramagnetic, so it points along the direction of the field you apply, and if you don't apply a field, it has no preferential direction. In a ferromagnet, however, you can train it such that all of the electron spins are pointing in one direction, even in zero magnetic field. Superconductivity is another example of just like interesting stuff that happens in materials. And so here I'm showing an image of a superconducting puck that's levitating over a track made of permanent magnets. So superconductors have two properties which are interesting. Their resistance goes to zero, which means that you're able to flow an electrical current without heat dissipating. And secondly, they expel magnetic field lines in something called the Meissner effect. And so that's part of the reason why this puck of superconductors levitating over this is because the superconductor is expelling magnetic fields, and therefore there's a repulsive force. In addition to looking at bulk materials, we can sort of take materials that we know and make modifications to them to probe different types of physics. And one of the tools that physicists like to use a lot is to reduce the dimensions of the world that the electrons live in. And so one example of this is graphene, which is a single atomic layer of carbon atoms. And so if you take electrons that normally live in free space and make them live in 2 dimensions or even 1 dimensions, like in a very skinny wire, like a nanowire, you can realize states of matter that you wouldn't normally be able to realize in 3 dimensions. And the last one, there's been a recent theoretical and experimental push to realize something called non-abelian anyons. And these are a type of quasi-particle where their quantum mechanical wave function on switching places of 2 of these particles behaves completely differently from anything we know of that exists in free space. And these also have possible applications in quantum computation. And the way that people have gone about trying to manufacture these, at least recently, is by taking multiple different materials and sort of smushing them together, because we want one property from a superconductor and another property from a semiconductor, and so you put them together and hope that their properties sort of mix. So it's a very, very hand-wavy way of putting it, but the materials that I'm studying, I will present here, are ingredients in possible realizations of these particles. Okay, so now I'm going to give a very abbreviated introduction to SQUID. So we use SQUID, so if you don't want to understand any of the technical details, we image the Z component, the out of sample component of a magnetic field on a local micron scale. And we do that using a superconducting quantum interference device, which stands for SQUID. So this is a schematic of the device here. The loop itself is a superconductor. In our case, it's made out of niobium and has two weak links, which are also called Josephson junctions. And we can apply a magnetic field to this device, and depending on how many field lines are going through this loop, the electrical properties of this device change. And they change based on the total amount of flux captured in the loop. So in a uniform background field, it corresponds to the background field times the area of the loop. In particular, if we flow a bias current through the squid, so it's just above its superconducting state, the voltage drop across the squid will be periodic in flux. And so by measuring the voltage and moving the squid over the sample, we can record that voltage and therefore something that's related to the flux of the sample. So our squids look a little bit more complicated. This is still sort of a cartoon, but you can see here that there's two Josephson junctions and there's two leads that we probe them. And I'm not going to explain this whole thing, but if we look at the front part here on the left, this is the part that gets close to the sample. So we have a pickup loop, and this is our main sensitive area, and this we bring very close to the sample, and our spatial resolution is sort of determined in part by the size of this pickup loop. And we stop magnetic field lines from going through the rest of the loop by putting a superconductor over them. So this superconductor acts much like the levitating puck over magnet and bends field lines around it so they don't go through the loop. Additionally, we have a field coil, which is concentric with this pickup loop that allows us to apply a local field to the sample. So here's a real picture of our squids. On the right is the full squid chip. So the active area is up here, and you can see it looks a lot like the cartoon I showed. And so we have electrical connections here that we can bond to and measure out the electrical properties of the squid. A couple of details about the squid. So the junctions are insulator superconductor junctions that are made up of niobium and aluminum oxide. And this chip itself is made out of silicon. And the squids that I used were made by Martin Huber at NIST, but we have a lot of new exciting squids from IBM that are working now. Our squids have very good flux sensitivity, which is microphinot per square root hertz. So in terms of currents, that means that we have a noise floor of a couple nanoamps per square root hertz. So we're really able to detect small currents with minimal averaging.
Sorry, I missed the reason why there are these two.
Oh, sorry. So this is just with the two pickup loops.
Yeah.
Yeah. So that is so when we apply a field with the field coil, that the applied field is canceled out. So the squid is counterwound, and so when we apply a field with the field coil, most of the applied field is canceled out, and we can just measure the field from the sample, the response of the sample. And it's also just to cancel out background fields. So here's a zoomed-in version of the tip of the squid, and what we have to do to bring it close to a sample is to polish down the silicon mechanically, which is every grad student in our group's favorite activity. And so the goal is to get it as close as possible to this area without breaking it off. And I think most of us have accidentally polished through this a couple times. And so our new squids, we don't have to do that, which is really nice, but we did have to do this for these experiments. Yeah, and so we take this chip that's been polished, we flip it over on the sample, and then we can move it using piezoelectric benders to scan over and record the flux as a function of position. And so one possible use of this is to look at the magnetic fields from current. So let's imagine a device that has current flowing along this edge of the device, and the current is indicated in blue. We know what the field lines look like from Biot-Savart law. They just go around the ring, or go around the current like this. And so if you imagine taking your pickup loop and sort of scanning it over the surface, when it's on this side of the current, it will see negative field lines going through, so it will record a negative flux. And when it moves to the other side, it will record a positive flux because the field lines are going up. So by looking for sort of the characteristic pattern of current flow, which is this plus minus flux signal, we're able to spatially resolve where currents are flowing in a sample. And this has been quite fruitful in the past couple of years. So these are the two experiments that I won't talk about, but we were able to image edge currents in mercury telluride, and these measurements in setup at least are very similar to the indium arsenide gallium antimonide measurements I'll talk about, but the conclusions are different. And in LaOSTO, which is a two-dimensional type of conductor, we found that there were enhanced conductivity. So red here indicates more current flowing and blue indicates less. And so we see these characteristic patterns at low temperatures of enhanced conductivity, which we attribute to the domain structure of the underlying STO. Okay, so this is the first experimental section of my talk. So first, I will give you some reasons why we want to study indium arsenide gallium antimonide. It's proposed to be something called a 2D topological insulator. Then I'll show you images of current in indium arsenide gallium antimonide and hopefully help you understand what this image is showing. And then we use our imaging capability to look at the properties of the edge states under different conditions and compare them to how we expect these interesting quantum spin Hall edge states to behave. And we find that in both the temperature dependence and in the dependence on the band structure that we're able to tune, that the properties of these edge states don't naively match what we expect for a 2D topologically insulating state. Okay, so I'm not going to give a full introduction to 2D topological insulators. It's quite a complicated concept to convey, but I'll try to give you an intuitive feel for how you make one out of the band structure. So in general, insulating materials can be characterized by a topological invariant when there's no field applied. This invariant can be 0 or 1 and just depends on the properties of your band structure. And it turns out that most materials we know of have a topological invariant of 0. And these are what we call trivial insulators. So for instance, the vacuum is a trivial insulator. And so if you imagine looking at the band structure, the energy levels of a trivial insulator, there's two bands. This is the valence band on the bottom and the conduction band on top. And if these are all occupied and these are all unoccupied states, then we have an insulator with the Fermi energy in the middle. And these particular bands have certain orbital characters. So the bottom band is derived from p-type orbitals, and the top band is derived from s orbitals of the atoms. And so the sort of recipe for getting a topological insulator is finding something that's trivial and then finding a way in your Hamiltonian to switch the order of these bands. And so in the case of mercury telluride, what you tune is, in a two-dimensional sandwich, you tune the thickness of a layer, and that leads to the order of the bands switching. And so this band inversion so now in the topological regime, the s orbital band is on the bottom and the p orbital band is on top. This sort of twist or band inversion that you're putting in the band structure tells you that you've gone through a trivial to topological transition. So how do we look at, or how do we probe in the real world, how do we probe the existence of a topological insulator? So in the two-dimensional realization, we make a device out of the topological insulator that has metal contacts, and on the sides there's some trivial insulator, and this can either be vacuum or some sort of substrate. And the experimental observable are the edge states, which have a special character. So they're called helical. Their spin is related to what direction they're going. So on the top edge here, the right moving electron has a spin up, and the left moving electron has a spin down. And so these are sort of half of what you expect for a normal 1D conducting mode, and they have some interesting transport properties. They live inside the insulating gap. So if our Fermi energy is in between these two bands, the middle of the sample is not conducting, but there are edge states which are approximately linearly dispersing, which can carry current. And so you can see if we apply current to the sample, the right moving states are sort of selectively populated over the left moving states. And if we were to image this, we would see that current is only flowing along the edges of the device. In transport, the signatures of this state are that you're in the insulator, it's not truly an insulator. And in fact, if these edge states don't have backscattering in them, you expect to get a resistance which is related to the geometry and fundamental constant, specifically h over v squared. Okay, so now we want to think of a real material where you can realize a state, and this material is indium arsenide gallium antimonide. So let's take a layered material, so this is a function of depth. And there's two insulators on the outside, aluminum antimonide. And then there's a thin indium arsenide layer and a thin gallium antimonide layer of the given thicknesses. And there's also silicon doping at the interface, which is a bit of a complication, but I'll get into what that does maybe a little bit later. So I'm not going to fully explain this diagram, but the bulk bands of indium arsenide and gallium antimonide are interesting in comparison to each other because this top band, indicated with this blue line here, of the indium arsenide lies below the bottom band of the gallium antimonide. So this is exactly sort of the thing that drives the band inversion that we're looking for to make a topological insulator. And so there's two. The other interesting thing about indium arsenide and gallium antimonide is that the electrons and the holes live in two separate layers. And so if we take a given thickness of indium arsenide and gallium antimonide and calculate what the electronic structure should look like, indicated by these dashed lines, we find that we do get the band inversion we want. The H1 band, the gallium antimonide valence band, lies above the indium arsenide conduction band. But we don't have an insulator anymore. There are states everywhere, so there's no gap. It turns out that we have to include tunneling between electrons and holes in order to open this gap. And so now we have this sort of weird looking energy gap, but there should be quantum spin Hall edge states that live in this gap. So now that layer profile I showed you is going into the board, and our collaborators use lithography techniques to pattern a device for us. So these are all connected to gold contacts. We flow a current from the left side to the right side, and we can also probe the voltage of the device across these 2 and 3. The other feature of this device is that there's a gold top gate, which is not electrically connected to the device, and this allows us to tune this Fermi energy. So initially this material is actually n-doped, so its Fermi level lies in the conduction band, but with an electrostatic gate we can tune it so it's in the insulating regime. And if we look at the resistance that we measured as a function of gate voltage, what we find is that at 0, gate voltage is very conducting, so it's sort of up in the conduction band. And as we tune to negative gate voltages, we see a peak in the resistance. And this peak indicates that we're tuning the Fermi energy through the gap. And so this is exactly the region where we expect to see edge states. So there's two weird features in this data. The first is that this resistance is much higher than the expected quantized resistance. And this is consistent with So this means that if there are quantum spin Hall edge states, there must be some scattering mechanism in them. And the second weird feature is that this sort of sweep dependence of the height. And we really don't quite understand that yet, but I will tell you which branch we're on. So let's image at different gate voltages. So if we go to the 0 gate voltage where we're sort of in the not insulating state, we expect the current flow to look pretty ordinary. So we're flowing current from left to right, and this flux image here shows a broad black lobe, which indicates negative flux, and a broad white lobe, which is positive flux. And so what we're seeing here is just a wide strip of current flowing in the device. And what we find is when we tune to the resistance peak, the flux image looks very different. In particular, under the top gate, which is from here to here, the current flow looks like it's flowing along the edges of the device. So you can see that there's a little white stripe here and a black stripe here, indicating that there's a line of current on the bottom edge. And on the top edge, the current traces out these voltage leads under the top gate. So it traces out the full device. So from now on, I'll be showing you current images as opposed to flux images. There's a neat numerical technique that we can do with knowledge of sort of our how our squid images fields in order to back out the total current density. So here I'm plotting we also get directional information, but I've sort of thrown that away for clarity, and so for simplicity, I guess. And so what I'm plotting is the magnitude of current flowing in the image. And so this reproduces what we can see from the flux images. At 0 gate voltage, there's just sort of a homogeneous strip of current flowing. And at the resistance peak, the current is flowing almost completely along the edges. So this color in the middle is close to white. So there's no current flowing in the hole, or in the middle of the device. So I want to analyze many of these images at the same time. And so one way of doing this is by taking a line cut across the data. So I'm just taking the magnitude of current flowing as a line across the sample. And so here's a plot of what it looks like for this image. And so there's two features that maybe aren't obvious here that you can see. The first is that the height of the bottom peak is twice as large as the top peak. So that's interesting, and I'll explain that in a minute. And the other feature is that these peaks have some width. And this finite width is not actually the width of the edge states, but it has to do with our squid spatial resolution. So now we want to image the sample under a variety of conditions. And so I'm going to just show you a couple of the things we did. So at low temperatures, it looks like the line cut I just showed, but as we raise the temperature of the sample from 4 Kelvin to 30 Kelvin, the bulk, the amount of current flowing in the middle here, rises up as we increase temperature, and the amount of current flowing in the edges decreases. Additionally, this sort of, yeah, sorry.
So just in terms of the units, is the current unit arbitrary or?
So here it is not. Sometimes I'll plot it in arbitrary units, but this is in normalized. So this is normalized to the total current flowing through the sample. So the integral over this line cut will be 1.
And the areas under the two curves are also different?
Yeah, so the total areas and the height, so that are proportional.
If they're the same width.
If they're, yeah, they're the same width.
But in any event, they're not the same.
Yeah, they're not the same. Yeah.
A little side peak to the side of the tall peak.
Yes, so that's good. Our point spread function is not exactly right.
Okay.
And so this is the leads of the point spread function not being exactly right. Okay, so we want to sort of quantify how much is flowing in each peak, so we don't just need to read off the heights. So we say, okay, our current can either be flowing in the top or bottom edges, or it can sort of be flowing homogeneously through the bulk. And then we generate what we expect the flux line cuts to look like and fit them. And they match qualitatively what we see in these images, or they just match what we see. So the bulk is rising and going higher as a function of temperature, so this is the total fraction of the current. And the top and bottom edges carry less and less current as we go to higher temperatures. And the other feature is that the bottom carries twice as much as the top at low temperatures, but they sort of equalize at low temperatures. And that feature has to do with the geometry of our sample. So we have these voltage leads here, and there's a very small amount of bulk material here. So if the bulk begins conducting, current can either go all the way up the edge and across, or it can jump across the bulk. So once the bulk starts conducting, these voltage lead edges are shorted, and the effective length of the edge where current is flowing is halved, and ends up being the same, approximately the same length as the bottom edge. And so this is the reason why we see this asymmetry at low temperatures when the bulk is insulating, and then they join together at higher temperatures when the bulk is shorting them. So now we want to try to get at what the resistance of the edges are, even though the bulk is conducting. And this is something that is a unique capability of squid, scanning squid. So we take this fraction of current that we extracted from fitting, and we divide the measured resistance by it. And so this is equivalent to assuming that we have 3 parallel resistors, the top edge, the bottom edge, and the bulk. And in this way, we can get at what the backscattering mechanisms in the edges are doing. What we find is that the top edge falls by a factor of 2, and we can explain that by this geometric factor that I mentioned. But the bottom edge, which doesn't have these voltage leads, is independent of temperature. And so this is telling us that the backscattering mechanism in the edge, if it's, is temperature independent. And we could also compare this to what's seen at transport at lower temperatures where the bulk is always insulating. And what we find is that over all of the measured temperature range, the resistance doesn't seem to have any temperature dependence to it. So here what I'm plotting is the resistance of each measurement normalized to the 4 Kelvin measurement. And just to show that, in transport at low temperatures, there's nothing really going on, and in our measurements, there's also nothing going on. So now we want to look back at this edge state, which has this weird spin structure, and think about what backscattering mechanisms are allowed. So the backscattering mechanisms are different from what you'd expect for a typical 1D state because you sort of only have spin up going one direction and spin down going the other. And so the easiest to understand mechanism for temperature independent scattering is single particle elastic backscattering. But this shouldn't be allowed in quantum spin Hall edge states, so we have to go look at other scattering mechanisms. So we can take into account inelastic scattering from phonons, or multi-particle scattering, or some more exotic things, and their temperature dependencies are all too strong to be consistent with our data. The closest to being consistent is this picture of sort of inhomogeneity in the bulk, forming quantum dots in which the edge states can sort of tunnel into and out of. And in a certain temperature regime, based on the size of the quantum dots and various other parameters, you can get a pretty weak temperature dependence of the resistance. I would still say that this natural log squared, or 1 over natural log squared dependence is not really consistent with what we see. So here are references for the scattering. There's been a lot of theoretical work on it. Okay, so we see this temperature independence is a little bit weird. So are we sure that we're seeing quantum spin Hall edge states or not? And so the question is, are we seeing like this unicorn that is quantum spin Hall effect, or is it something that's sort of trying to impersonate it? And the way that we hope to do that is by tuning the band structure. And so this picture I showed you before gives you this sort of weird looking band structure that should have edge states. But if we can in situ tune the band structure so we untwist these bands and get rid of the band inversion, we should be able to get a non-inverted trivial insulator, and there should be no edge states in this regime. And because the holes and electrons live in different layers of the indium arsenide gallium antimonide, we can tune the band structure just by applying electric field, which is pretty neat. So all we need is an extra gate on the bottom, and then we can independently tune whether the gap is inverted or non-inverted, and we can also tune whether our Fermi level is in the gap or not. And theoretically, they predicted what states you would see as a function of backgate and topgate voltage. And you see that you get a phase diagram where there's a small region that's gapped, that's the trivial insulator, and then if you tune from positive gate voltage to negative gate voltage and keep your Fermi level inside the gap, that you go to what should be a topologically insulating state. So our collaborators at HRL made us such a sample, and the transport looks, at least, with some rose-colored glasses, similar to the phase diagram that we see. So there's sort of this peaked region on the right at positive gate voltage, and we attribute this to the trivial or non-inverted band gap. And then there's also a very light region here, which is inverted.
Eric, do you want someone to turn the lights off?
Yeah, it's probably not going to help super. Yeah, so it's still not so great. So this feature is very subtle, and the reason that is because in this sample there's no silicon doping at the interface, and so the features here are obscured by residual bulk conductivity in the indium arsenide gallium antimonide. So really, and I don't know of anyone who's been able to get this full phase diagram in a silicon doped sample as of yet.
So that's not the same sample?
No, this is a different sample made by different people. And so, I've sort of labeled these regions based on how they look, but there's been a lot more work looking at magneto transport Hall effect that is, I think, pretty convincing signatures that this is the trivial regime and this is the sort of inverted regime. And so let's first look at the inverted regime, and what we see is that current's flowing all throughout the sample, but there's a slight enhancement along the edges of the device. And we've also measured unsilicon doped samples from our other collaborators that look very similar to this. And so this is consistent, at least, with quantum spin Hall edge states and a conducting bulk, which arises for weird reasons. So now we take our gate voltage from negative to this weakly resistive region to the inverted regime, and what we find is that the current in the non-inverted regime is completely carried by edge states, which is not what you'd expect for quantum spin Hall edges. So that's quite surprising, and it's been shown in transport that these edge states can actually mimic the quantization effects that you expect to see. So by using scanning squid, we can think about how do these edge states in these two different regimes connect. And so I took images or line cuts as a function of backgate voltage across the phase diagram, going all the way from sort of deep in the non-inverted regime to deep in the topological regime. And what we find is there's no region in this phase diagram that doesn't have edge states. In other words, the edge states here that we know, we're pretty sure we think that the origin of these must be trivial. As we tune the gate voltage, these edge states never go away. So this is not to say that these edge states don't have some quantum spin Hall component to them, but we really need to think carefully about what the role of these trivial edge states is in the transport regime in the topological region. Yeah, so I'm a little bit behind, so I won't go into this fully, but this is one possible origin of trivial edge states is something called band bending. And the point I just like to make here is that the band gap in these materials is extremely small and orders of magnitude smaller than the sort of normal scale of band bending in indium arsenide. Although those values are taken in a different configuration, it's not too hard to imagine a situation in which the band bending sort of bends farther than the gap. Okay, so just told you what conclusions are. So in the remaining, I said 25 started. Yeah, so the remaining amount of time I'd like to tell you about relatively recent measurements that we've performed that are looking at something called a current phase relation. So I'll introduce that by telling you what a current phase relation is. And then I'll talk about the material that we're studying, which are indium arsenide nanowires. And then I'll talk about our results, which show that the shape of the current phase relation fluctuates wildly as a function of gate voltage. And then I'll try to tell you what we can learn from those results. So the question I'd like to pose is, what happens when you smush a superconductor and not a superconductor together? Well, if the not a superconductor is normal metal or a semiconductor, it's conducting. And it can communicate with the superconductor through a process called Andreev reflection. So if you imagine that there's a normal electron heading towards this interface, it can reflect and reflect as a whole, and then a Cooper pair, which are the fundamental charge carriers in a superconductor, can go in the other direction. This is a phase coherent scattering process, so this allows the quantum phase of the superconductor to be transmitted into the normal metal. And this sort of conveyance of phase information into the normal metal is what allows the superconductivity to sort of leak into the normal metal. And the normal metal will inherit some of its superconducting properties. And this is called the proximity effect, or the superconducting proximity effect. So if we imagine making a slightly different device, which has two superconducting leads on the left and right, and then a short section of some normal material, or let's say a nanowire, the two superconductors can communicate with each other through Andreev reflection, so they can communicate phase information from left to right. And in this way, actually, we can get even though this is not normally superconducting, we can get into situations where a supercurrent, which doesn't have any resistance, flows across this normal material. And so these sort of, I've drawn sort of a semi-classical picture of electrons going one way and holes going the other way, but if we think about this as a quantum mechanics problem, we have a normal material, which has some confinement, and then we have weird boundary conditions. And so what actually forms are bound states. And these Andreev bound states are what carry superconductivity in the normal material. If we can independently tune the superconducting phase of each lead, the properties of these Andreev bound states will change because you're changing sort of the boundary conditions by tuning the phase difference between the two leads. And so here's just an example of the sort of energy spectra you get from Andreev bound states in a short junction limit. So if you have a perfectly transmitting normal material, such that none of this phase information gets lost as an electron travels from one superconductor to the other, you get states that look like this as a function of phase. And so you can see that they have some shape, and the energies range all the way from the gap to 0, and 0 being the Fermi energy here. If we then take this normal material and introduce some scattering into it, another way to think about that is in a scattering formalism that the transmission of a normal electron through that material would not be 1. And so if the transmission is non-zero, you sort of open up a gap in these states, and so the Andreev bound states are a lot less sharp, and they also don't go all the way to 0. So if you can somehow apply this phase difference and then measure the current that's flowing across the junction, what you get is the derivative of the energy with respect to the phase, at least at 0 temperature. And so if we look then at the current flowing through this Josephson junction, this superconductor, normal superconductor junction, for both of these cases, we see that the shape of the current versus phase, or the current phase relation, is different. And so here, the current flowing through the device has a sharp, almost discontinuity. Sorry, I should mention that this energy is the unoccupied energies. So if we look at the energy here, we're looking at this branch here, and when we get to pi, we switch over to this branch. So there's a big change in the sign of the derivative, and therefore a big discontinuity in the current phase relation. And by measuring the current phase relation in this junction, which has some scattering in it, you see that there's some remnants of this sharp discontinuity in that the sine wave is sort of tilted this way, and that's what we call forward skewed. But it's much less sharp, and also the amplitude is smaller. And so the idea is that we can probe properties of the Andreev bound states by looking at the current phase relation. Here's a schematic of our junctions. They're made up of a semiconducting indium arsenide nanowire, and they have a thin coating of aluminum on them. And then the coating of aluminum, some small section of it is etched away to form the Josephson junction. And the reason we want to study these materials is that they're of interest for realizing, or one of the reasons is that they're of interest for realizing these non-abelian anyons that I referred to earlier, specifically Majorana quasiparticles. And they're quite nice for this because the interface between their superconductivity, or the superconductor, and the semiconductor is very close to atomically perfect, as you can see from this transmission electron microscope image. And the properties of the superconductor as probed through tunneling show that the sort of behavior of the superconductivity in the nanowire is sort of better in some abstract sense than if you were to just evaporate aluminum on here. Yes, so the way that we want to tune the phase is by putting this junction into a loop and then applying a local magnetic field and threading a flux through this loop. So this flux will apply a phase difference across the junction. So for a squid, that means that we can tune the phase drop across the junction by putting a current through our field coil. Then the current phase relation of the junction will result in a circulating current around the ring, and we measure the signal from that current using our pickup loop. And so here's a optical image of our device. So you can see that there's a loop here and there's a nanowire junction down here. And the other feature of the most recent sample that I've measured is that it has a bottom gate. So there's a gold pad underneath with some dielectric, and then the nanowires on top of that. So that allows us to tune how many electrons are in, what the density of electrons in the nanowire, and look at how the current phase relation changes as a function of that. We're able to image many samples because not only can we see the current phase relation by the circulating current, but we can also see the diamagnetism, or the repulsion of magnetic fields, due to sort of the evaporated aluminum ring. And so we can sort of navigate by looking around and looking for these ring features, and then center the squid over them so that we can measure the currents. So first I'm going to just show you a couple of current phase relations that we measure. This is sort of a typical one. And so the two features I'd like you to notice is that it has some amplitude, which is 50 nanoamps, and this amplitude corresponds to the critical current you would measure of the junction if you were to do a transport experiment. And the second is the shape of the current phase relation. And so for a normal sine wave, you expect the peak to be pi over 2. And if you look at where the maximum is, it's ahead of pi over 2. So this is a forward skewed current phase relation. And most of the current phase relations we measure are some degree of forward skew. If we tune the gate voltage on the same ring, we can get different behavior. And so this is actually the most forward skewed current phase relation. So you can see this looks nothing like a sine wave. It looks more like a sawtoothy sort of thing. And you can see that the maximum here is very close to pi as opposed to pi over 2. And so this looks a lot more like the case of a perfectly transmitting Andreev bound state, as I showed earlier, and this one looks more like one that has some scattering. So we want to take this sort of shape that we can get out of by looking at the current phase relation and quantify it. And so we do that by fitting to a harmonic series. So there's a first harmonic and a second harmonic, which has twice as many periods, et cetera, et cetera. And then we add all of these up, and we can get some arbitrary periodic shapes. In particular, this is the function we fit to, and just in the interest of disclosure, I allow the phases of the different harmonics to vary with respect to each other, which is due to instrumental reasons, which I'm happy to get into. But for most of the measurements that I'm showing, these are constant. The result of this is constant in the fits. But for some of the data, it's necessary to sort of shift the harmonics slightly with each other to take into account the shape. And it's useful to separate out the fitted ring characteristics in this way. So we pull out A1, which is roughly the amplitude of the current phase relation. And this amplitude is sensitive to systematic errors of our squid. So if we've positioned slightly to the left of the center of the ring and I don't know it, I'll underestimate the amount of current flowing in the ring. So this has some 10% order error bars on it. The shape, however, doesn't really depend on where the squid is, and so these features, A2 over A1, A3 over A1, convey only the shape information and not the amplitude. And we'll sort of focus on analyzing this for the most part. And just to give you some intuition about what these values tell you, I think A2 over A1 is the most important one, and this is a proxy for how much the maximum has shifted far away from pi over 2. So for 0, we get just a sine wave, but if it's some small negative number, we get that the maximum is slightly ahead of pi over 2. And you can see for this very forward skewed, we get a very large negative value for A2 over A1. Especially in these more forward skewed, we get a lot of harmonic information, at least 5 harmonics. And so comparing the higher harmonics to what we expect from theory is something that will allow us to sort of check the validity of what how we're interpreting our data. It also fundamentally changes how the shape looks. So now we measured current phase relations as a function of bottom gate voltage, and this is just a small region of the data. And so I'd like to just point out a couple things. So I've added an arbitrary offset to separate the data. And this is about where the nanowire sort of turns off and there are no longer any modes. As you can see, especially at low gate voltages, there are strong amplitude fluctuations, but there's also very strong shape fluctuations. So here we have one that's not so forward skewed, or this one maybe, and then only 2 gate voltages away is the most forward skewed current phase relation we see at any gate voltage. So both the shape and the amplitude of the current phase relation are changing really quickly and wildly as we tune the back gate voltage. And so we can tune to higher and higher back gate voltages, and we also, for some reason, see a weird backward skewed current phase relation, which I'll probably not have time to get into, but this is something that we really didn't expect to see, and is a bit puzzling. So then we can fit all these current phase relations, there's a lot more data that I'm not showing, and extract the different harmonic components. This is roughly proportional to critical current, and we can see that there are fluctuations in A1, and they're also in A2, A3, so we can resolve a lot of harmonics, and the fluctuations are in all of the harmonics to some degree. And if you sort of try to match up features, for most of the features, they seem to at least partially track. So now we want to think about just what the shape is doing, because this is sort of the new information we're getting by doing scanning squid, or by measuring the current phase relation. And so what we find is that the shape itself is also fluctuating, which is what we saw by just looking at the data. And at low gate voltages, it's fluctuating very wildly. So here's the 0.4, very forward skewed, and then it goes almost down to 0, and sort of, it's a bit crazy. So the other feature I'd like to point out is that, okay, there are error bars on these, but the error bars are much smaller than the fluctuations. And the broad features tend to be repeatable, at least on small gate voltage sweeps, but in the details, and there's slight heights changes and stuff. So we also see fluctuations in the higher harmonic sort of shape parameters. We also looked at a bunch of different rings without gating. And so here I'm showing a CPR. Each of these is from a different ring with a different junction, and they have slightly different lengths, between 50 and 250 nanometers. And I've just ordered the current phase relations in order of increasing amplitude. But you can see here also that from junction to junction, sort of the amplitude varies and also the shape sort of. So here's a pretty forward skewed one, and there's one with a similar amplitude that's not quite as forward skewed. So if we look at this A2 over A1, which characterizes the forward skewness as a function of length, what we see is that there is maybe some slight downward trend indicating that the shape of the current phase relation is getting less forward skewed as we make the junction longer, which could be due to the fact that the transmission of the junction should get less as we make it longer. But the main feature is that for nominally identical junctions, the shape parameter varies considerably. And so we attribute this sort of junction-to-junction variation to the same mechanism that must be causing the fluctuations as a function of backgate voltage. We also looked as a function of temperature at a fixed gate voltage. And so you can see that we can read off the critical temperature by looking at where A1 goes to 0, or the critical current goes to 0. And it's slightly below what we'd expect for aluminum, but reasonable, I would say. And then as we track the different harmonic components, as we go to lower temperatures, close to TC, there aren't any other harmonic components. And this is sort of from Ginsburg-Landau theory, you get a sinusoidal current phase relation. So near TC, sort of whatever's weird and going on at low temperatures, it must sort of become sinusoidal at high temperatures. And you can also see that this non-sinusoidal shape or higher harmonics only show up at low temperatures. And again, we can plot sort of the shape. So this is minus A2 over A1 and A3 over A1. And you can see that they grow strongly as you go to lower and lower temperatures. And this is sort of from the, if we take this Andreev bound state picture in a short junction, this is what we expect, but the exact shape doesn't exactly match. Okay, so now, well, I'm not going to make that joke, but like any good scientist, we have a hypothesis after we've taken data. So let's imagine that we have a perfect interface, or a perfect junction in some abstract sense, not abstract. So we have a perfect junction in the sense that there's no barrier at the normal superconductor interface, and there's no scattering in the junction. What do we expect to see in the shape of the current phase relation? And so this is sort of not exactly simulating the physical situation we have. I can get into exactly why it's not, but it's sort of qualitative features I think should be correct of this simulation that I'm doing based on this reference. And what we see is that there are fluctuations in the shape of the current phase relation. Each of these individual fluctuations corresponds to another conducting mode or another Andreev bound state entering the junction. So as it enters, it doesn't immediately enter with a perfect forward skewed shape. It sort of starts off as like sine and morphs into this forward skewed shape as we tune Fermi energy. And so if we're measuring the total shape, we sort of see fluctuations in the shape. And as we add more and more modes, the fluctuations get smaller because most of the modes are this forward skewed shape and the relative contribution of the new mode is small. So what happens if we add reflections at the interface? So the way that we do that is by putting delta function potentials basically at the SN interface. I've chosen interface transparency, which gives us roughly the same shape that we observed in the measurements, which corresponds to a transmission of about 0.85. And what we see already is there's a lot more structure to the shape of the current phase relation. So we see a lot of sort of peaks and valleys, and as you add more and more modes, it gets sort of more complicated and the amplitude of the fluctuation falls. And these sort of fluctuations are due to Fabry-Perot, or I guess they're just Fabry-Perot resonances that form due to this sort of well that you've set up. And so the simulation I've done is, I think, is on approximately the same energy scale based on the number of modes to this data set here. And so we can see, the qualitative features, the fact that the fluctuations sort of die off as you add more modes, and sort of weird, fluctuation behavior is reproduced, but the sort of scale of the fluctuations in energy seems much higher in our data than in the simulation. So we probably have to take into account some more complicated disorder other than just interfacial reflections, but there's plenty of possible origins of this, and in particular doping, accidental doping of the nanowire, or probably charge traps in the gate dielectric. And so for now, we're not going to be able to reproduce our data by sort of figuring out the right places to put disorder, so I'm going to zoom in on a couple features and portions of the data and try to understand them a little bit more. So the first is the fact that the fluctuations sort of decrease as a function of gate voltage as we add more modes. So what I've done is I've swept the gate at different temperatures, and what we find is that the scale of the fluctuations decreases as we go to higher temperatures for similar gate voltages. So here I've taken where the critical current first becomes non-zero and subtracted it. This value is slightly different between the data sets. And if we go back to the simulation and put in temperature, what we find is that this also happens for these sort of resonant states that are formed by interfacial barriers. So both the scale of the fluctuations sort of gets smaller as you add more and more temperature, and also the overall skewness falls as you go to higher and higher temperatures. The second feature that I'd like to point out is at low gate voltages, where we see very peak-like behavior. And so the fact that we have this sort of, conducting, superconducting region that's surrounded by two regions which go very close to zero makes me think, so we have peaks instead of sort of fluctuations at low gate voltages, and so we want to sort of think about resonant states as opposed to conduction through conducting, a critical current through conducting states. And actually, if we zoom in at the low Fermi energy data of the simulations, the sort of shape of the resonances here that we see are pretty well reproduced actually by the data. In particular, the sort of sharp cuspy nature in this A2 or A1 parameter is well matched by the simulation. And also, there's sort of an asymmetry to the shape of this peak, which is also reproduced here. And so this makes me think that even though it can't just be interfacial scattering probably that's leading to these resonances, that we're sort of on the right track, that the qualitative features of these peaks match what we see, but you can see that the positions don't. I'd like to note that actually this peak here on the larger gate sweep is where we observed the most forward skewed current phase relation. So the most forward skewed current phase relation is weirdly sort of just as the junction is turning on, where we'd expect disorder to be sort of the most important naively. And so I attribute this sharp forward skewness not to a really conducting or close to perfectly conducting mode. Instead, I think it's because of resonant tunneling. And it actually gives you a similar shape if the tunnel barriers are the same, give you the same tunnel rate. And so here, I'm taking what you expect for a perfect transmission mode at the temperature we measured and just plotting it on top of the data. So there's no fit parameters here. And you can see that it doesn't match perfectly well. Actually, the A2 or A1 parameters are exactly the same for these two, but their shape is different because their higher harmonic parameters are different. And so you could either try to adjust the transmission to lower values to account for this, or you could also adjust the temperature. So the base temperature is taken by reading a thermometer far away, and the temperature for electrons is not necessarily the same. And so what I've done is I've allowed the temperature to vary to see if we can get a shape that looks correct. And we actually get what I would say is a reasonable electron temperature as measured through other means in the same fridge. We got similar values. So if we allow the temperature to vary slightly, it looks like we have a perfect transmission mode that's at 130 millikelvin instead of 30 millikelvin. And if I take this transmission and I set it to 0.99 instead of 1, the fit actually gets worse, even if I allow temperature to vary. And so I'm not saying that we have a perfect transmission mode, but it seems like we have a very, very transmitting mode, which is due to sort of accidentally formed resonant or quantum dot behavior at low gate voltages. Yeah, okay, so we also saw a backward skewed current phase relation, which is just very weird and just weird. And doesn't really come up, if we think about just Andreev bound states, you don't get backward skewed current phase relations. And so this is something that we're still looking into, but if I sort of zoom in on the region where there's a dip, you can see there's a finite region where there's sort of a transition from forward skewed to a weird backward skewed current phase relation. And it is almost coincident with a minimum in the critical current, but not quite. And so the only speculation I have as to that is that in SIS junctions, sometimes in very weird, so superconductor, insulator, superconductor junctions, you can get this weird shape. And so it's possible that if we have sort of this picture of disorder in the nanowire, that we have one strong point of disorder at the center, which acts as a single tunnel barrier, and that might lead to this sort of behavior. But sort of need to figure out if we can recreate this maybe in a more artificial way and study its shape in more detail. I'd like to briefly discuss the implications of this work, which I'm still sorting out because this is fairly new, but even in sort of a high quality nanowire with this close to atomically perfect interface and a fairly high transmission coefficient, fluctuations dominate the shape of the current phase relation at low gate voltages. And in particular, it seems that sort of Fabry-Perot or quantum dot-like resonances match the observed current phase relation behavior at low gate voltages, and so it's possible that the sort of large fluctuations in shape are sort of due to these accidentally formed resonances in the nanowire. The scale of the fluctuations, however, is a little bit too quick to, at least in my mind, to be explained by just sort of interface effects. So we must probably also have to think about other sources of potential barriers. And there's quite a bit of, well, not quite a bit, but there's data analysis techniques in which you have to assume a current phase relation, in particular interpreting how a junction behaves as you apply a field. And this is just sort of a word of caution that if you're doing Fraunhofer measurements and trying to fit them using a sinusoidal current phase relation, that's probably not right. And the shape of your current phase relation could depend on a millivolt scale change in the gate voltage. And so and it's not always what you expect. So you could have a backwards skewed current phase relation that would affect your Fraunhofer pattern in some weird way. And so, there should always be caution in sort of applying the sinusoidal current phase relation approximation to interpreting data. So I'd just like to acknowledge collaborators and thank you for listening.
Questions?
So that backwards relation, current phase relation, did you see that in more than one ring, or was that only in that
This is
one
the
ring? where
only
you struck
place
the gate
we see it.
voltage?
We only see it in this, so this range is smaller than the gate voltage spacing of the other data that I showed.
Okay.
So it was lucky that we happened to land on it, and I suspect that if we did like a very dense series, we might find other regions where that's the case. But this is the only place we saw it. And so we measured, I think we measured hundreds and hundreds of current phase relations as a function of gate voltage, but also 30 different rings
30 rings.
without gating, and we don't really see them in any of the,
And what was the thickness of the rings?
in which, so that,
So I'm not sure how they were made. You were talking about epitaxial growth.
yeah,
there,
so
but you talked about the length.
these nanowires sort of grow with the epitaxial aluminum on them, and then we evaporate an aluminum ring on top of it. And so the evaporated aluminum is a couple hundred nanometers, I'm assuming. Yeah.
And the epitaxially grown nanowire?
The epitaxially grown layer is thinner, tens of nanometers. So that's information I need to get out of my collaborators.
And that arm going away from that is aluminum?
This is gold. So there's a little tab here. And actually, if you go close to TC, you can see that the inverse proximity effect from the gold kills superconductivity here, like 10 millikelvin before superconductivity everywhere else does.
So that tab doesn't keep your electron temperature lower? You've got like a bigger tab out there. It's not an isolated
Yeah, so
ring.
it's not isolated, yeah, but yeah, the filtering in the fridge has gotten. Yeah, I need to double check whether this line is filtered or not. But our fridge no longer has a radiation shield, and so that might have something to do with it. Yeah.
For the features you saw in the indium arsenide gallium antimonide, in particular the temperature independence and what happens in the trivial regime, how do these compare to mercury telluride?
It's a good question. So in the squid data that we took that's similar to the indium arsenide gallium antimonide, the temperature dependence is also very weak. in the edge states at high temperatures. There's not particularly great published resistance versus temperature data for the edge states. It seems to be weakly varying, although it's not strictly constant. We did measure mercury telluride quantum wells that are thinner, and we don't see trivial edge states that are as conducting as the edge states we see in the topological regime. And there's, in re-looking at the trivial edge state data, there might be some very weakly conducting edge states, sort of N-type edge states, but more sort of, that's something that only in like learning how to analyze this data better, we're able to see in the data, and their conductivity is at least an order of magnitude higher than that of the edge states we observe in a similar device. So I think something, there's certainly also this MIMS data that shows that there's trivial edge states when you go to high field. So and I think if you look at that data, there's also indications in the non-inverted samples of like slight edge state type conduction in the N-type region. So I think that's a feature that should be investigated more, but it's not quite as clear cut as, look, there's edge states that are just as conducting.
Any more questions in the public session? No? We'll have more questions after a 5-minute break then.
Great.
Yeah.
Thanks, everyone.
Thank you.